Kia ora and welcome to this video on question 1 of the 2013 Scholl Calc paper. This year's exam had 6 questions, of which you could choose any 5. Over the next week we'll look at all 6 questions. This first one here is fairly reasonable. It involves using a mathematical model to approximate a Prince Rupert drop. The formula looks a bit messy. We're first up asked where the drop is the widest, so that's an optimization question. We're looking in part B at where the concavity is 0, so we're locating a point of inflection. And then the third question revolves around a solid of revolution and explaining why the volume of the solid has an upper limit. So before we get started, I'm just going to show you this model in 3D using a GeoGebra diagram. I didn't create this one, I just searched up on GeoGebra online, solids of revolution, but I typed in the function in the top left there, which is the function we're dealing with. So we've got this drop, and we can see that it's widest at the point 0 to 1, and we need to find the y value at that point. However, in 3D, when we consider this curve being rotated around the x-axis, we're over here on the right hand side. The width of the drop is widest. We need to actually find the highest y value and the lowest y value. It's the difference between the top and the bottom. Because of the symmetry of the curve, it's actually just 2 times the biggest y value. When we take a curve and we rotate it around the x-axis, we get a solid of revolution. What we're essentially doing here, if I just move these limits, is we're taking an area, and in this case I've got the area between 0 and 2.6, and we're rotating that area around the x-axis. And if we do that and extend the tail up to a large number, we get the volume enclosed inside the drop. On the right hand side there, it tells us the volume is some fraction of pi, and it turns out that fraction there is tending towards a constant. It's not like it goes off to infinity even if the drop gets longer and longer and longer. Okay, so back to the maths. When you find area, so for example, if we wanted to find area below this curve, we would take a thin slice of area. Okay, and that thin slice of area is approximately a rectangle because the y values are approximately the same. The width of the rectangle is dx and the height of the rectangle is y, where y changes as x changes. So what we have is y times dx, and then the integration, an integral symbol there, it looks like an S, and it turns out that when you integrate between limits, so I might go here between 0 and 6, I'm finding the area because I'm adding up all of those rectangles of y times dx. So area equals that. This symbol here, which is an integral, you can think of it as like an infinite sum, and that's why the integral symbol looks like an S. So that's for finding area, but the part C of the question asks us to find volume. So then what we need to do is think about this area being rotated around the axis, and that would generate us something like that. Our cross section would then be circular. The radius here would be y. The thickness of these discs would be dx, and the area of what we're integrating, the area is pi times y squared. That's the area of a circle of radius y, and of course the radius changes as y changes. And if we integrate this and times it by dx, that's the thin's thickness. So essentially this here is a thin cylinder or disc, and the integral in here says add them up. So if we add up all the discs, we get volume because we're adding up an area there times by dx, which is a small volume. Okay, so a thin cylinder is like, you can think of it as dV, whereas before we had y times dx, and that there is like dA, a small rectangle of area A. Okay, so that's how volumes work. Volumes are no longer in level 3. They used to be NCA level 3. They got taken out. So if they want you to find the volume in a scholarship paper, they're going to give you the formula. And for this question, actually, they did. Down in the last part there, they say the volume is given by the integral of pi y squared dx. You're not expected to derive that just using it. Okay, first part. We've got this mathematical model, which looks like an ugly formula. Turns out it's not too bad. Phi is a constant. It's the golden ratio. And we need to find the widest point of the drop. Okay, so in other words, find the maximum value of y and double it, because remember that we're considering it in a 3D setting where it's been rotated. Okay, so to find the maximum y value, it's a optimization question. We're differentiating that curve. Y equals, I'm going to pull a square root phi out the front. Square root phi out the front of this thing, because it's a constant, it's not going to affect the derivative. And then the other factor is e to the minus x, take away e to the minus 2x, all to the power of 1/2. So if we're diffing this, dy dx, the square root phi just stays there. In terms of chain rule, the half comes down the front. We drop the power to negative 1/2, and then we need to times by the inner function differentiated. The inner function differentiated, e to the minus x, differentiates to minus e to the minus x, and then the second term differentiates to plus 2 e to the minus 2x, and we need that equal to 0 to find the maximum y value. The first factor, this is never 0. Okay, it's never 0, it's actually 1 over the square root. 1 over the square root cannot be 0, so we're looking at solving this dude here equal to 0. Okay, so solving that, we have e to the minus x would need to equal 2 e to the minus 2x. And then if we divide through, we can go 1/2 e to the minus 2x divided by e to the minus x. It's a kind of reverse cross multiplication there. And then we can subtract the powers because the bases are the same. They're both base e. E to the minus 2x divided by e to the minus x. Minus 2x, take away negative x. E to the minus x. Log both sides. Log of 1/2 equals minus x. Use natural log because it's the opposite of base e, and then x is equal to negative ln 1/2. Now that might look a bit suspicious because we know our x value is between 0 and 1, according to this bit here. However, log of 1/2 is a negative number because anything between 0 and 1, the log function is negative. So negative ln 1/2 is actually the same as, oopsies, I'm writing with a highlighter, haven't done that in a while. This is also equal to ln of 2. Okay, think about that, the minus can go up the top there and make it 1/2 to the power of negative 1. The reciprocal of 1/2 is 2. So ln 2, which turns out to be 0.693. Okay, let's see if we've answered the question. Where is the model drop the widest? Okay, we've got that x value, and how wide is it there? So now we need to use this value and find the y value. So go back to our original function, root phi, e to the minus x, okay, x is ln 2, minus e to the negative 2 ln 2 to the half. Okay, all I've done is subbed in the x value, ln 2, up into x in the expression. We have to do the same sort of maths here with the minus needs to go up the top there, and the minus 2 goes up the top there. That will enable us to simplify the log stuff. So we've got e to the minus ln 2, which is the same as e to the ln 2 to the negative 1, minus e to the ln 2 to the negative 2. Okay, the e and the ln's are inverse functions, so they can cancel. And then we end up getting root phi times 2 to the minus 1, which is 1/2, minus 2 to the minus 2, which is 1/4, to the half. 1/2 minus 1/4 is a quarter, and we've got the square root of that. Square root of a quarter is a half, so we end up getting root 5 or 2. Remember that our width is 2 times the y value, so the width of this drop is root 5. Now if you worked in decimals throughout that would be fine as well, but the reason pulling the root 5 out at the start was just to make the derivative easier, but it turned out quite nice in the fact that the answer was just the square root of that, or the constant is at the front, which is kind of cool. Okay, part B. The drop changes shape near B in figure 1. This is a bit misleading because if you look at B in figure 1, it still looks concave down. It's curving downwards, and then after B it's curving downwards. It doesn't look like it's changed concavity through B, but they are referring to this point here, we call that B, where it is curving downwards and then afterwards it's curving upwards. So there's a point of inflection that we're looking for. Actually, the diagram's a bit dodgy. Looks like it's about there. It's close to 2. We don't have to differentiate twice. Normally, to find a point of inflection, you'd find the second derivative because they've already given it to us. Use the second derivative is equal to this expression to find the exact x-coordinate of B. Okay, so to do that, just go second derivative. Root 5 e to the 2x minus 6 e to the x plus 4. You might want to derive this to prove that you are able to differentiate twice and rearrange stuff. Equals 0, concavity equals 0. Remember that the second derivative gives us concavity, like the first derivative gives us gradient. This is equal to 0 if that numerator is equal to 0. It's a disguised quadratic equation. If you let u equal e to the x, then you have u squared minus 6u plus 4. It doesn't factorize, but you can complete the square in it. U minus 3 all squared, take away 9 plus 4. Minus 9 plus 4 is negative 5, put that on the other side. 5, square root both sides, 3 plus or minus root 5. And looking at the diagram there, we know that the answer is around 2. U is equal to e to the x, so x is equal to ln of 3 plus root 5. It's not the negative because 3 minus root 5, 3 minus root 5 is actually, gives log of a negative. No, it doesn't. 3 minus root 5 is 0.76, and if you take the log of that, you get a negative number. We know x is not negative. So this gives us 1.6556 to 4 dp. We were told to find the exact value of this expression. So we need to keep with the log bit. Find the exact x coordinate of B. That is the answer. And maybe a justification, not x equals ln of 3 minus root 5, which is less than 0. Okay, third part. The volume formed by rotating a curve between x equals a and x equals b is given by this expression. Show that the volume is equal to this. Now they're integrating between 0 and ln p, so that choosing the lower limit to be 0, which is the left end of the drop, but they're choosing an upper value to be some number ln of p. Now that increases as p gets bigger. A log function is an increasing function, so increasing p increases ln p. But the reason I've chosen the upper limit to be ln p is, it makes me thirsty, ln p. They've chosen that because of the e part of and the fact that e and ln are inverse functions, and so it tidies up, it makes it a really nice expression. So to find the volume, we're integrating between 0 and ln p, pi y squared dx. We could pull the pi out the front straight away, out of the integral, because it's a constant. And our y expression, remember, is the curve we started with, but we're integrating y squared, so we can get rid of the square root there. There's going to be a phi times by e to the minus x minus e to the minus 2x. And that's what we get when we square that. If we then pull the phi out the front of the integral as well, it's also a constant, so just make a little bit of room there. And then we need to integrate this with respect to x. So it's not a bad question. E to the minus x antidiffs to itself divided by -1 minus e to the minus 2x antidiffs to itself divided by -2. And that's between ln p and 0. You have to be careful with definite integrals when you sub in 0. With polynomials, when you sub in 0, they often go to 0, but e to the power of -0 is not 0. Let's just tidy up the negatives for a start. We've got negative e to the minus x minus plus a half e to the minus 2x. It just looks a little bit tidier. Okay, now ln(p). We need to put ln(p) into this expression first. So we've got negative e to the minus ln(p) plus a half e to the minus 2 ln(p). That's the first substitution. Then we subtract. It's a definite integral. We now sub in 0. Okay, we're going to play exactly the same game as the earlier questions. The minus goes up the top there. The minus 2 goes up the top there, so that we can then cancel the e and the ln's. Because I'm trying to get it into this format that the answer requires. So we've got the e and the ln will cancel. We're going to have 1 over p. And then for the other one, we're going to have half times 1 over p squared. And then the e to the 0 is 1, so we're going to have plus 1 minus a half. Okay, tidying all of this stuff up. We've got minus 1 over p plus 1 over 2p squared plus a half. Now I'm going to pull a p and I'm going to pull a 2 out of the brackets in the denominator. Okay, so I pull that out of the thing because this had a p, but it didn't have a 2. So if I pull a 2 out of the top, I need to actually times the top and the bottom of that fraction by 2. So I get minus 2 there. Because the minus 2 over 2p is equal to minus 1 over p. This one here is just going to be... Actually, do I want to pull out... I'm going to pull out a p squared, actually. And then that's going to be p. This one's going to be 1. And this one's going to be p squared. Okay, and the reason I've done that is because now I can factor this. We've got a perfect square. And then we can see as it's p minus 1 all squared divided by p squared. So I can write that as p minus 1 all over p squared. We actually had the answer correct, like up here. Often with scholarship, the messy algebra stuff is just proving the result in the form that they require. So that's it. And the reason why we've done it this way, it's quite useful to us. It's a question, the last part of the question says, explain why the volume of the drop is never more than some upper limit. So if we increase that tail as long as possible, and we'll tend it off to infinity, the volume doesn't get any bigger than some limit. And if you think about this expression here, this is the volume of the drop from 0 to ln p. If p tends to infinity, ln p tends to infinity, so that's an infinite tail. So we want the limit as p tends to infinity of the volume expression. Now if p gets really, really large, this minus 1 here does absolutely nothing. P minus 1 is pretty much p if p is really large. And so we get p over p there, which is 1. So the limit of that whole bracket is 1. 1 squared is 1. So the limit of this volume is equal to pi times phi over 2. That is the maximum volume. Okay, catch you in the next video.